industry has hit a wall with static scaling. Simply stacking hundreds of unique layers is a mathematical dead end, where each new billion parameters yields diminishing returns in actual reasoning. OpenMythos is a theoretical reconstruction that attempts to map what many believe is Anthropic's secret internal architecture. It suggests a way out of the scaling trap. The central hypothesis is that Claude is a recurrent-depth transformer. It doesn't rely on the visible, token-by-token chain of thought we see in other models. Instead, the heavy lifting happens in the dark. Deep reasoning occurs silently within a continuous latent space before the first token is even generated. In this system, a specific subset of layers is recycled. The model runs the hidden state through the same weights multiple times in a single forward pass, effectively deepening the network without increasing its size. We can derive how this works by looking at the linear time-invariant dynamical systems math, the stability constraints preventing training collapse, and the mechanics of overthinking. Recurrent depth architectures decouple reasoning depth from parameter count. This allows for deeper reasoning chains while keeping the model footprint manageable. The process is governed by a recurrent update rule. The network recycles its weights to update the hidden state, HT, at every loop iteration t. This equation reveals the core mechanism. The encoded input E is injected into the hidden state at every loop. Constant injection at t equals 1, 2, and 3 prevents drift, keeping the original prompt focused across every level of recurrence. In a standard model, chain of thought is a single committed path. The model outputs a token and must build on it, even if it's a mistake. Latent looping is different. Because it operates in a continuous space, the model can maintain and update multiple alternative reasoning branches simultaneously. This acts as a breadth-first search over the reasoning space. The model explores different directions in parallel during the forward pass. It can evaluate complex logical structures and resolve them internally, outputting the final result without needing intermediate tokens to show its work. This architecture enables systematic generalization, the ability to apply known rules to entirely novel situations. Most transformers are limited by their training data. They struggle when asked to combine knowledge in ways they haven't explicitly seen. To reach this reasoning, looped models undergo a three-stage grokking process. First, the model simply memorizes the training data without understanding the underlying logic. Then, a sudden phase transition occurs. The loss plummets to near zero as the model achieves systematic generalization. This suggests that advanced reasoning isn't a gradual improvement. It is a structural threshold reached through iterative looping. Training these models is notoriously difficult. Without the right constraints, looped transformers suffer from catastrophic instability and sudden loss spikes. We can diagnose this by treating the architecture as a discrete linear time invariant, or LTI, dynamical system. This vector field shows residual explosion. The bounding hypersphere represents the unit circle of stability, governed by the spectral radius of parameter A. If this radius reaches 1, the hidden state breaches the circle, exploding into chaotic noise as training diverges. The fix, outlined in the parquet architecture, is to guarantee stability by construction. We parameterize A as a continuous negative diagonal matrix. By discretizing the system using Euler schemes, we can mathematically enforce that the spectral radius stays strictly below 1, regardless of the training noise. This ensures the model remains perfectly stable throughout training, allowing for the massive scale recurrence needed to unlock deep, complex reasoning. At inference time, we encounter a different limit. Running more loops doesn't always lead to a better answer. This is the overthinking problem, where the model's accuracy actually drops if it recycles the data too many times. As tokens circulate, the hidden state can drift past the optimal solution, degrading the representation. For simple inputs, the model must quickly identify the answer and eject early. If trapped too long, the token state fragments into noise, destroying the prediction. The solution is adaptive computation time, or ACT. ACT uses a learned halting mechanism for each position. It monitors the convergence and decides when to stop looping. This enables continuous depthwise batching, where easy tokens exit early and difficult tokens continue to loop within the same batch. This transforms the architecture into an adaptive system, where the computational budget is allocated based on the mathematical difficulty of the task. When we synthesize these components, the prelude, the looped recurrent block, and the coda, we see a highly efficient reasoning engine. To handle wide domain knowledge, the recurrent block likely uses fine-grained mixture of experts. As tokens loop, they are routed to different experts at different depths. This evolves the computation without adding more parameters. This achieves the performance of a massive model using only a fraction of the parameters. However, there is a trade-off. This architecture prioritizes recursive reasoning over rote memorization. It is built for logic, not necessarily for factual recall. The future of these models isn't just about making the stacks higher. It's about moving towards these compute-adaptive dynamical systems. If this saved you time, hit subscribe. We review tools like this every week, so you're always ahead. Now, if you liked this deep dive into RNN architectures, you're going to love our breakdown of Mamba. The shift from discrete token generation to continuous latent trajectories changes how we think about machine reasoning. We are moving from static weight stacks to active dynamical systems. I'll see you in the next one.